Black holes weighing a billion suns should not exist 700 million years after the Big Bang. The math doesn't work. And for 2 decades, nobody could explain how they got that big that fast. A paper published this month might have just caught one of them in the act. So there's a fundamental problem in astrophysics that doesn't get nearly enough attention. We've known for years that the early universe contains supermassive black holes that are way, way too large for their age. Not a little too large, absurdly too large. And the James Webb Space Telescope has made this problem dramatically worse. Here's why. A black hole grows by eating gas. Pretty simple. But when it eats, it shines. And that radiation pushes gas away. So the more it eats, the harder it becomes to keep eating. There's a natural cap on how fast a black hole can grow. It's called the Eddington limit, named after the astronomer Arthur Eddington, and it works basically like a speed limit for feeding. At maximum speed, a black hole doubles its mass roughly every 31 million years. Now do the math. Take a black hole born from a dying star, maybe 100 times the mass of the sun. Give it the full Eddington growth rate. Start the clock 200 million years after the Big Bang, when the first stars formed. By the time the universe is 700 million years old, you get about 7 million solar masses. That sounds impressive until you realize we keep finding black holes at that same age that weigh a billion solar masses. You're off by a factor of 100, minimum. That's not a rounding error. That's a crisis. And JWST keeps finding more of them. A black hole at redshift 7.64, meaning 670 million years after the Big Bang, weighing 1.6 billion suns. Another one at redshift 10.6, just 430 million years after the Big Bang, already accreting 5 times above the supposed speed limit. One astrophysicist compared it to walking into a delivery room and finding a fully grown adult. So the question that's been haunting this field is simple. How? How do you build a billion solar mass monster in less time than it takes the Milky Way to rotate once? There are basically 3 ideas. The first is that these black holes started bigger. Instead of forming from a dying star at 100 solar masses, maybe some primordial gas clouds collapsed directly into black holes weighing 100,000 solar masses, skipping the star phase entirely. That gives you a head start, but the conditions for that to happen are extremely specific and kind of exotic. The second idea is that they started small but somehow broke the speed limit. Super-Eddington accretion. Eating faster than physics says you should be able to eat. Theorists have been proposing ways this could work for years, but we'd never actually caught a black hole doing it. Not at the edge of the observable universe. Not at the time when it actually matters. And then there's option 3, which is some combination of both. This is where JWST comes in. And this is what makes this new paper genuinely significant. JWST was first spotted in 2022 by astronomer Seiji Fujimoto and colleagues. They found it hiding in archival Hubble data of one of the most studied patches of sky in all of astronomy, the Goods North Deep Field. Thousands of astronomers had looked at this data before. It was sitting right there. But it didn't look like a typical quasar. It wasn't bright and blue. It was red, dusty, and buried inside what appeared to be an extremely active star-forming galaxy. Fujimoto's co-author Gabriel Brammer put it perfectly at the time. It was hidden just in front of you. They suspected it was something special, an embryonic quasar still wrapped in its birth cocoon. But Hubble couldn't confirm it. They needed better tools. Fast forward to February 2026. A team of 27 researchers led by Chinyue Fei and Fujimoto published a new paper using every major instrument on JWST, NIRCam, NIRSpec, and MIRI, plus millimeter wave data from the Noema Observatory. And what they found is striking. Using deep spectroscopy, they detected a broad emission line from hydrogen gas whipping around at over 2,200 kilometers per second. That speed is the fingerprint of gas orbiting close to a massive black hole. From that measurement, they derived a black hole mass of about 35 million solar masses, and they measured its feeding rate at 2.7 times the Eddington limit, 2.7 times the speed limit. That number matters more than it might sound. See, this isn't the first claim of super-Eddington accretion from JWST data. There was a big splash about an object called Elid 568, where some researchers initially claimed accretion 40 times above the Eddington limit. That number got revised downward pretty quickly, and there have been other borderline cases where the data was noisy or the interpretation was contested. But 2.7 is different. It's not wildly extreme. It's not a headline designed to grab attention. It's right in the range that theoretical simulations have been predicting for decades as physically sustainable. Not a one-time burst, but a rate that a black hole could plausibly maintain for millions of years. And when you plug that number into the growth equations, something clicks. At 2.7 times the Eddington limit, the black hole's doubling time shrinks from 31 million years down to about 11 million years. Starting from 35 million solar masses at this point in cosmic history and maintaining even moderate super-Eddington feeding, this black hole reaches 1 billion solar masses well before redshift 6. It gets there with hundreds of millions of years to spare. That's the first time we've had a real, observed data point that closes the gap. Not a theoretical model, not a simulation, an actual measurement of a black hole growing fast enough, at the right time, in the right way to explain the monsters. But there are two more things about JWST that make it even more important than the feeding rate alone. The first is its relationship to its host galaxy. Almost every other high redshift black hole that JWST has found has a weird problem. The black hole is too big compared to the galaxy it lives in. Sometimes 10 times too big, sometimes 100 times. Sometimes the black hole is as massive as the entire galaxy. That's bizarre because in the local universe, the relationship between a black hole and its galaxy is remarkably consistent. The black hole is typically about 0.1% of the galaxy's stellar mass. It's one of the tightest correlations in all of astrophysics, and it seems to hold across wildly different types of galaxies. JWST has been finding early universe black holes that violate this relationship dramatically, which raises an uncomfortable question. Are these black holes going to eventually settle onto the local relationship? Or is the relationship itself not as fundamental as we thought? JWST sits right on the local relationship. Its black hole is about 0.1% of its galaxy's stellar mass, which means this isn't just a black hole growing fast. It's a black hole and a galaxy growing fast together, in lockstep, both at record pace. The galaxy itself is manufacturing about 330 new solar masses worth of stars every year. That's roughly 200 times the rate of the Milky Way today, and it's doing it in a region about 30 times smaller. Imagine the entire star formation output of 200 Milky Ways crammed into a volume the size of the galactic core. The gas density, the radiation, the violence of it is almost hard to comprehend. The second thing that makes JWST special is what it represents in evolutionary terms. For years, cosmological simulations have predicted a sequence. A dusty starburst galaxy eventually bursts a quasar that's initially buried in dust. Over time, the quasar's radiation and outflows blow the dust away, and it emerges as a luminous blue quasar, the kind we've been observing for decades at slightly later cosmic times. Dusty starburst to red buried quasar to blue luminous quasar. That's the predicted life cycle. We had plenty of examples of the end stage, the bright blue quasars at redshift 6 and 7. And JWST has found hundreds of compact reddened objects called little red dots that might represent the earliest buried phase. But nobody had found the thing in the middle, the object actively transitioning from one stage to the next. JWST is that object. It's a red quasar still embedded in its starburst cocoon. Brighter than a little red dot by a factor of 10 to 100, but redder and fainter than a classic blue quasar. It's the caterpillar mid-metamorphosis, and catching it in this brief phase, predicted to last maybe a few million years out of a galaxy's billion-year lifetime, is extraordinarily unlikely, which is exactly why it took this long to find one. Now, I want to be honest about the limitations here, because this is a preprint. It has not been peer-reviewed yet. The numbers could change. The black hole mass estimate comes from a single spectral feature, a broad hydrogen emission line. That's standard practice, but single epoch mass estimates carry uncertainties of a factor of 2 to 3. The Eddington ratio of 2.7 could realistically be anywhere from about 1 to 7. If it's closer to 1, JWST is still interesting, but less revolutionary. There's also a paper from January 2026 by Watson and colleagues in Nature arguing that electron scattering in dense gas can artificially broaden emission lines, making black holes appear more massive than they really are. The JWST team argues their object is different enough that this effect probably doesn't apply, but it's a legitimate concern. And then there's the most obvious caveat. This is one object, one system. You can't rewrite astrophysics based on a single data point. The discovery team themselves acknowledge this, though they also point out that finding JWST in a relatively small survey area suggests these objects aren't impossibly rare. There should be more out there. What's encouraging is that more data is coming. Fujimoto, now at the University of Toronto, has been awarded 356 hours of JWST time in Cycle 4. That's an enormous allocation. The team plans to get deeper spectroscopy to nail down the black hole mass, search for outflows that would confirm a young quasar clearing its surroundings, and map the neighborhood around JWST in detail. And that neighborhood is itself pretty fascinating. Preliminary data suggests JWST sits in an exceptionally dense region of the early universe, a proto-cluster environment packed with merging galaxies, dusty starbursts, and other red compact objects. Think of it as a cosmic construction site. The raw materials for extreme growth, dense gas, and frequent collisions are all right there. So let me put this in context. What JWST is building, discovery by discovery, is essentially a biography of the universe's first black holes. Different objects are snapshots of different life stages. At redshift 10 and above, you have the infancy. Tiny or already mysteriously massive seeds just beginning to feed. Then come the little red dots, the awkward adolescence, hundreds of shrouded black holes apparently outgrowing their host galaxies in ways we don't fully understand. JWST is the critical growth spurt, a black hole and galaxy co-evolving at maximum velocity, on track to become the kind of luminous quasar we've observed for decades. And then at redshift 6 and 7, the fully formed adults. Billion solar mass monsters dominating everything around them. The satisfying part is that this doesn't require new physics. No modifications to general relativity, no exotic particles, no overturning the Big Bang. It's the existing physics applied more violently than anyone expected. Dense gas, frequent galaxy mergers, and feeding frenzies that push just past the speed limit, sustained for just long enough, in just the right environments. Think about that for a second. Every photon from JWST traveled 13 billion years to reach JWST's mirror. Longer than Earth has existed. If you compress the entire history of the universe into a single calendar year, JWST existed on January 20th. Our sun didn't ignite until September. The dinosaurs went extinct at 11:39 p.m. on New Year's Eve. And in that impossibly remote January, in a violent pocket of a young universe, a black hole roughly 9 times heavier than the one sitting quietly at the center of our Milky Way right now was gorging itself beyond its speed limit inside a galaxy that was building almost a full sun's worth of new stars every single day. We weren't supposed to be able to see this. The phase is too brief. The object is too dusty. The universe was too young, but it was there the whole time, in one of the most studied patches of sky in history, just not looking like what anyone expected a quasar to look like. Sometimes the answer isn't hidden in the darkness. It's hiding in plain sight, wearing a disguise. Want to keep up with the latest science discoveries that change how we understand the universe? There's always something new, and lately, always something stranger.